Hi, I'm Arjun Singhvi, and today I'm going to describe Whiz, an execution engine that enables data-driven analytics execution. Data analytics frameworks are used in diverse settings by many important applications to analyze large data sets. However, we observe that the underlying execution engines hinder performance and efficiency due to numerous issues such as intermediate data unawareness, execution engines resorting to static parallelism and intermediate data partitioning, and adopting compute-driven scheduling and data organization. This led us to asking ourselves the following question. How do we overcome all of these limitations pertaining to compute-centric execution engines, which resulted in Whiz? Before getting into the details of our solution, let us understand a typical job execution pipeline in data analytics frameworks today. Consider a data analytics framework, be it graph or stream or batch. The high-level execution flow is the same. The user submits their job using a high-level interface. Then, the internal planner of the framework converts the submitted job to a logical graph in which the vertices represent the different stages and the edges represent the dependencies. For example, in case of a word count job, the logical graph consists of one map stage and one reduce stage. The logical graph then undergoes a number of optimizations to finally give a physical graph which encodes low-level execution details such as the number of tasks per stage and dependencies between them. In case of our word count example, the physical graph consists of n and m tasks corresponding to these two stages respectively. This physical graph is then handed over to the execution engine which orchestrates its execution. In case of our word count example, it first launches the map tasks which generate intermediate data organized in one partition per reduced task, which the execution engine routes to the appropriate reducer for further processing. Let us now look at the limitations of today's frameworks in the context of batch analytics. Similar limitations arise in the context of graph and stream analytics as well. As we've seen, the execution engine does the intermediate data management. However, it has limited runtime visibility into intermediate data, and thus it cannot change the processing logic of a task based on intermediate data properties. Further, task parallelism and intermediate data partitioning strategies are decided at job submission time and cannot adapt to runtime changes, in which case the skew between data partitions can degrade performance as tasks have unequal work assigned, and the job execution cannot adapt to runtime resource changes. Further, decisions regarding when to execute tasks of downstream stages are based on the static compute structure. For example, most systems today deploy consumer tasks once X% of upstream tasks are done. Consumer tasks start pulling data, and the idea is that the remaining producers would be done in the interim. However, this may lead to consumer tasks idling when they are waiting for the remaining data to be available, which may take longer time than expected, say due to skew. While analytic frameworks suffer from several additional issues, details of which are in the paper, we observe that these limitations are due to the compute-centric nature of the execution engines, which tightly couple data and compute and are agnostic to intermediate data. This in turn leads to the execution engine to early bind to a physical graph and tie intermediate data organization to the physical graph. Moreover, the task computation logic is determined before the job is handed over to the engine. Several prior works have observed similar limitations and have proposed point fixes to a subset of these limitations. However, with Whiz, we overcome all the limitations of compute centricity in a unified manner through a ground-up redesign. With Whiz, our approach is to make intermediate data and compute equal entities during job execution by a clean logical separation between the two. The execution service manages computation and the data service manages intermediate data. I will now discuss the three key ideas of Whiz. The decoupling enables intermediate data awareness. Consider a job submitted to Whiz. The execution engine initiates the execution of the root stages and pushes the intermediate data to the data service, which is responsible for its management. This allows the data service to gather custom properties of the intermediate data at runtime, which enables driving all aspects of job execution based on data properties as we see next. Moreover, it intrinsically provides cross-job storage isolation and avoids I/O hotspots. For example, consider another job submitted. In this case, the data service can enforce cross-job policies as it manages intermediate data across all jobs. Building on this data visibility, Whiz, unlike existing execution engines, incrementally decides the task parallelism and size at runtime based on data properties. For example, consider a job submitted to Whiz. The data service can make the collected statistics available to the execution engine, which can then decide whether to launch one task or more and further decide the resources allocated to each task. This late binding enables Whiz to handle intermediate data skew and adapt to resource flux. Further, Whiz schedules computation only when intermediate data meets predefined execution predicates. For example, the data service can notify the execution engine when some partitions of the data meet the predicate, and then it can launch the task to process them. This leads to efficient use of resources. Moreover, Whiz also uses the obtained data visibility to determine the exact task logic at runtime. Having looked at the three key ideas, let us now contrast the Whiz job execution pipeline to today's frameworks. Firstly, the compute-centric execution engine is replaced via Whiz. Like before, users still use the same interface to submit jobs, which are then converted to a logical graph. However, after that, instead of generating a physical graph, each stage of the graph is annotated with execution and modification predicates and is handed over to the execution engine. Execution predicates determine when data is ready to be consumed by a downstream stage, and modification predicates determine which processing logic should be chosen at runtime. With the aid of these predicates, Whiz incrementally generates the physical graph at runtime in the following manner. It transfers the logical graph, which encodes the dependencies and modification predicates to the execution service, and data properties to be collected along with the execution predicates to the data service. Then, the execution service initiates the execution of root stages and pushes the intermediate data into the data service, which further notifies the execution service when data is ready to be processed. Having looked at the overall execution pipeline, let us now delve deeper into the data service. A key responsibility of the data service is to organize the intermediate data generated from a stage. Whiz uses a linear time, rule-based heuristic to pick machines so as to maximally meet our objectives of load balance, data locality, and fault tolerance, details of which are in the paper. And then we initialize each machine with a fixed number of partitions. In this manner, the data organization is no longer tied to the compute structure, which minimizes within job skew across tasks and avoids hotspots, enables rapid task processing, and minimizes failure recovery times. Moving on, let us now briefly look at the execution service. Among other things, the execution service needs to decide the task parallelism and placement. To do so, it groups ready partitions subject to an upper bound in the following manner. Consider two machines with these ready partitions, each represented by a specific color pattern combination. First, we group local data partitions, as can be seen. We then group each remote data partition. In our example, the blue data partition is spread across both the machines. We add in more partitions to the group subject to the upper bound. And then we group any remaining partitions. Each group is processed by a specific task. This approach minimizes cross-task queue and data shuffling, leading to improved performance. Let us now look at how Whiz performs. We built a Whiz prototype by modifying Tez and Yan and evaluate it on a 50-machine cluster by replaying TPCDS queries and PageRank jobs, and measure the job completion time and make span. First, we compare Whiz against other batch analytic frameworks. The x-axis shows the factor of improvement in job completion time, and y-axis shows the job distribution. We see that Whiz improves the job completion time by 1.2 times on average and 1.75 times in the tail. Next, we compare Whiz against graph analytic frameworks, and we see a similar trend in the job completion time improvements. Additionally, we see that Whiz improves the overall make span by a factor of up to 1.4x. Similar trends hold true even for stream analytics, details of which are in the paper. Delving deeper, we observe that the gains come from more rapid processing due to data-driven execution and better data management. Whiz is able to schedule more tasks due to more data local tasks which finish quicker. The graph shows the number of tasks over time for batch analytic workloads. Additionally, we observe that Whiz avoids intra-stage skew within tasks, and it avoids storage hotspots as the data service load balances the data across the entire cluster, as can be seen in the graph which shows the per machine data distribution over time. Additionally, for graph analytics, we observed that the ability of Whiz to determine optimal parallelism at runtime, especially for high-degree vertices, improves performance. This is possible through execution predicates that deem a partition to be ready once it receives 1000 messages from neighboring vertices. Apart from this, we also observe that modification predicates and fault-tolerant data organization also improve performance, details of which are in the paper. In conclusion, we find that the compute-centric execution engines hurt flexibility, performance, and efficiency by their tight coupling of compute and data and being agnostic of intermediate data. We designed Whiz, a data-driven execution engine that drives all aspects of execution based on intermediate data properties. It makes compute and data equal entities by logically decoupling them and brings in intermediate data visibility. Thank you very much for your attention, and I look forward to answering your questions.